So in the last session, we gave a proof to the isomorphism extensions theorem. The theorem says that if sigma is an isomorphism from a field F to F prime, and if E is an extension, algebraic extension of F, then the sigma can be extended to E to a subfield of F prime closure. So this was the theorem which we proved in the last session. So today we'll do some immediate results. We'll discuss some immediate results of this theorem. So let E be an algebraic extension of F, and alpha beta belongs to E be conjugates. Then there exists a conjugate isomorphism psi of alpha comma beta from F alpha to F beta. We know that. So what we have here is there is an isomorphism psi alpha comma beta from F alpha to F beta. This is our sigma, and of course this is a extension of F, and this is also an extension of F, and we have a F prime F closure here, and and E is an extension of algebraic extension of F, and since alpha belongs to E, F of alpha is a subfield of E. So E is an algebraic extension of F of alpha. So when we apply this rule, we can find a tau alpha beta from E to tau of E alpha beta, and this is a subfield of F prime closure. So the result is the conjugate isomorphism can be extended to E, extended from E extended to an isomorphism from E to a subfield of F closure. Let us do an example on this. So we'll take our base field Fs is equal to Q, and root 2 and root 3, so root 2 and minus root 2 are conjugates. So there is a conjugate isomorphism root 2 comma minus root 2, that is from Q of root 2 to Q of minus root 2. So let us assume that E is equal to Q of root 2 comma root 3. So what is the definition of this psi? Psi of root 2 comma root 3 root 2 minus root 2 minus root 2 of a plus b root 2, because this is the general element in Q root 2, is equal to a minus b root 2. So that is the definition of this. Now we want to extend this map to this is an algebraic extension, definitely. Q root 2 and root 3 are algebraic extension of Q root 2. So how do you extend this? When you extend this map to here, then when we apply an element on Q root 2, it should give the same result as the element mapped by psi of root 2. So what is the general element here? So let us define tau from Q of root 2 comma root 3 to a subfield of subfield. I'm going to just write as a subfield. So how do you define an isomorphism here? Tau of a plus b root 2 plus c root 3 plus d root 6 equals see what happens here is equals a minus b root 2, because all root 2's should be converted to minus root 2. You can have c root 3 minus d root 6, because here there is a root 2. So this is one of the extensions. There are more. So let us say another extension would be a plus b root 2 plus c root 3 plus d root 6 equals a minus b root 2. This 3 here, it is mapped to root 3, but you can map root 3 to minus root 3 also, then also it will be an isomorphism. So you can write it as minus 3 root 3. So then this will become plus b root 6. So this is another one. So we can extend this psi root 2 comma minus psi root 2, psi root 2 comma minus root 2 to either of this. So let's say this one is tau 1 and this is tau 2. So the extensions of psi root 2 comma minus root 2 are tau 1 and tau 2. We'll do one more example. Let us take E is equal to Q of root 2 comma root 3 comma root 5, and our F is Q of root 2 comma root 15. Definitely E is an extension of, is an algebraic extension of F. So this is going to be Q of root 2 comma root 3 comma root 5 and Q of root 2 comma root 15. And we are going to define a map from Q of root 2 to Q of root 2 15 by see, when you define, you can use the generators to define the isomorphism. These are the generators of this field. So you can say sigma of root 2 is equal to root 2 and sigma of root 15 is equal to minus root 15. This has to be a conjugate. Otherwise, this will not be an isomorphism. So when you define like this is the full definition of the isomorphism. You can also write it as, take an element from here and map it to that. So both are equivalent. So let us find out all the algebraic extensions, all the extensions of sigma. So you can extend the sigma to a tau of Q of root 2 comma root 3 comma root 15 root 5, and which is an extension which is a subfield of the closure of Q. So if you want to, when you define this one, you can define like this: tau of root 2 equals tau of root 3 equals tau of root 5 equals. So that is this is a complete definition of this isomorphism. So let us say our problem is find all extensions of sigma from Q root 2 comma root 15 defined by sigma of root 2 is equal to root 2 and sigma of root 15 equals to minus root 15. So when you want this to become the extension of sigma, then you don't want to change this. Root 2 should be always root 2. Because that is how it is. You cannot change to minus root 2. But here there is an option. You can either have root 3 and minus root 5, or minus root 3 comma so the extensions of, there are two extensions for sigma. Of sigma are, let's take this tau 1, this is tau 2, or tau 1 and tau 2. Let us do one more problem on this extensions. See, x cube minus 2 is irreducible in Q of x. And one of the roots or zeros one of the zeros of p of x is cube root of 2, and this is a real number. This is a polynomial of degree 3, so there are at most 3 zeros for this polynomial, but there is only one real root. There are other 2 real roots. They are -1 plus I root 3 by 2 and -1 minus I root 3 by 2. You can find out this one by dividing x cube minus 2 by this, and you'll get a quadratic polynomial. Then use minus p plus or minus root of 4ac minus by 2a. You'll get this. So when you say the cube root of 2, this is actually a real zero of x cube minus 2. The complex zero of x cube minus 2 are these two. So we'll write it like this. Let alpha 1 is equal to cube root of 2, comma, alpha 2 equal to -1 plus I root 3 by 2, and alpha 3 is equal to -1 minus I root 3 by 2 are zeros of x cube minus 2 in Q of x. What does this mean? This means that alpha 1, alpha 2 and alpha 3 are conjugates, because the irreducible polynomial of these 3 elements are same. Now our objective is, we'll take an identity map Q to Q, identity map. So we want to extend this to, Q of cube root of 2 comma root 3. Definitely this is a algebraic extension of Q. 2, a subfield of Q closure. So our question is, find all the extensions of the identity map identity isomorphism from identity isomorphism to an isomorphism from Q of cube root of 2 comma root 3 to a subfield of Q prime. That is our problem. So when we want to find out an isomorphism from here, as I said before, we can define the isomorphism by giving values to cube root of 2 comma, cube root of 2 equal to root 3. What are the conditions? This is an identity isomorphism from Q to Q. That means these two values will never come here. So you can give any values here. Any values that will make tau1 an isomorphism. That's the only restriction. Because this cube root of 2 and cube root of 3 does not affect the identity map. These two are outside Q. That's why. So instead of writing cube root of 2, I'm going to write it as alpha 1. So in order to make tau1 a isomorphism, this has to be mapped onto a conjugate of alpha 1. So let us make it as alpha 1, and this also have to be, second one will be tau2 of alpha 1 is equal to alpha 1, tau2 of root 3 is equal to minus root 3. The next one would be tau3 of alpha 1 is equal to alpha 2, because that is possible, these are conjugates, and tau3 of root 3 is equal to root 3. And tau4 of alpha 1 is equal to alpha 2, tau3 of root 3 is equal to minus root 3. The next set will be tau5 of alpha 1 is equal to alpha 3, tau5 of root 3 is equal to root 3, tau5 of alpha 1 is equal to 3, and this is going to be 6. Tau6 of 3 equal to minus. So these are the 6 possible extensions of identity map from Q to Q to an isomorphism from Q of cube root of 3 to cube root of 2 comma cube root of 2 to a subfield of Q closure. So we'll discuss one more quick results from the isomorphism extension theorem. So let F closure and F prime closure be two algebraic closures of a field F. So there is a field F. So I'm going to repeat again two closures of this same field here, but the closures we are going to assume that they are different. Okay. Now we need to find out the relation between these two different closures. So there is an identity map from F to F, and this is an algebraic closure of F. So we can extend this I to a tau to a subfield of, we'll write it a subfield of, we'll write it like this, a subfield of F prime closure, and that is T of tau of F closure. Using the isomorphism extension theorem. But here, this is a tau is an onto isomorphism. So consider an inverse. So inverse is actually coming from tau of f prime to a subfield of f closure. Right? So actually subfield of f closure, actually this is actually not the subfield of f closure, it is actually f closure. And this is also an onto isomorphism. So this can be extended, we are assuming that this is a subfield of f prime closure. So f prime closure is somewhere here. So we can extend this one to another isomorphism, let's say tau bar, to a subfield of f closure. But this is already an onto function. It is already onto. So if you are extending this one to a subfield of this, that implies tau of f closure is equal to so that means algebraic closures of a field are isomorphic.